My name is Paulo Lopes and I'm a principal software engineer at Red Hat. And on top of that, I am an open source developer mostly for the Vert.x project. If you want to later on get in touch with me, there are the links for Twitter, GitHub, and my LinkedIn account. So today I'm talking about latency. So what is latency? In a way to try to explain the concept, the latency is the reason why we need animations like this. Like things take too much time, and then we need to have some animations to show that, okay, you need to wait. To put it in a bit more, to put it in a way a bit more self-explainable, the definition of latency from encyclopedia is that network latency is a term used to indicate any kind of delay that happens in data communication over a network. So in layman terms, latency is the time that it takes for a request to go from your computer to a server, and the time that it takes to the data to come back from that server back to your computer. So if you sum the two times, you have the latency. So the main I think I skipped the issue with latency is that it's nothing new. Like it is known that latency is a problem for many years. And for example, I have here a couple of links in 2006, Amazon wrote a report saying that every 100 milliseconds of latency on their web pages, it cost them 1% in sales. So, in the same year, Google created another report where they said that every extra half-second increase in their search page generation time, the traffic to their website dropped 20%. So if you're thinking, how does it apply to me? If you're working on e-commerce or any application that users need to interact a lot, you know that people don't like to wait. And a more recent report about financial services, that you can see the link there, says like a broker can lose $4 million in revenue per millisecond if their electronic trading platform is 5 milliseconds behind the competition. So latency is really important thing to worry about. What is important here is that I want you to take home that latency is not a problem. Latency, it's the symptom. It's a symptom of your system. So you cannot solve latency, but you can solve why your application suffers from it. So, and again, lots of people have already researched how to handle latency, and InfoQ has a very good set of articles, and there is this one from 2007 from Dan Pritchett, where he wrote about the problems with latency and how does it affect systems. And then he came up with a list of ideas, architectures, changes that we should apply to our designs to overcome latency. So he wrote down that basically we should write loosely coupled systems based on loosely coupled components. We should use asynchronous interfaces when we need to communicate between these components. It also applies to all the I/O that your application does. He wrote that we should horizontally scale from the start, because you can start building an application, and if later on the implementation process you decide, okay, now I need to add clustering, that will be quite hard task to implement, but if you think ahead of time that you should support it, then it becomes easier. He also wrote that we should use active architectures not standby architectures. Like all systems should be active all the time. And finally, he also wrote that probably you should adapt base instead of ACID shared storage mode, because most of the times when we talk about databases and storage, we go with the ACID because we want the safety of the transactions and the consistency of the data. But for many applications, this is not really necessary. This is why technologies like NoSQL are so popular, because the basic availability, soft state, and eventual consistency is good enough for many applications. So in 2011, Tim Fox created a project called Vert.x. When he created the project, he created the definition that Eclipse Vert.x is a toolkit for building reactive applications on the JVM. And if you look at how the project is built, basically he decided that we should use loosely coupled components on our architecture, and this is guaranteed using the event bus. So the event bus, you can think of the event bus as like a very simple messaging system that passes messages between all your components for you. It uses asynchronous interfaces because all our I/O is done using Netty, so we don't block at the I/O level. And it horizontally scales from start. So with a command line flag, we enable a cluster mode, and then the cluster mode is SPI, where you can use a very common unpopular frameworks like Hazelcast, Apache Ignite, and so forth. So the question is, why non-blocking I/O? Why is it so important to think about non-blocking I/O? So think of this example for 1 second. Imagine that these blocks are requests on your application, and your application takes 5 milliseconds to answer a request. So a request comes in, 5 milliseconds, second request, third request, fourth request, 5 requests. So in a perfect optimal scenario, we can say that one thread of our application will be able to handle 200 requests, and one thread nowadays is nothing. Think, for example, that our laptops nowadays have 8 cores or even more. So if your laptop has 8 cores, then it will be able to answer to 1600 requests per second. But the request time will start growing as threads need to start fighting for execution time. So what you start observing as you start adding more load to your system is that, like, first request comes in, it's executed, second request comes in, and it's paused somewhere in the middle. A third request comes in, it's paused again in the middle. A fourth request comes in, it's executed. And then you think, why is my application pausing? And if you have a bit of skills using command line tools and Linux, you can do something like this, like PS AUX. And if you search for the 8th field that comes from the output of this command, and you search all the lines that the field is with the value D, and this is very, very, very important. The D comes from the Linux kernel, so it's just a detail. So if you look at the D, you'll see that your application is mostly waiting on sleep, waiting for I/O. So it's not doing anything. So now, for example, the data came back from the database, and the rest of the request can be executed and returned. Another request comes in. And now finally the second request is completed. However, like in reality, things get a bit harder, because as load comes in, more things are involved. So the first request comes in as before, and then there is some activity that is performed by the operating system and also by the JVM, which is context switching. So the application needs to stop the current running thread save its state in memory, so saving CPU registers, memory value stack somewhere in RAM, switch to another thread, then execute, and then there's some fight for resources, so it cannot complete. Again, switch to another thread. So the third thread runs, again fights for the database, and it doesn't complete. Switch to another thread, completes, so forth, and then we even have situations where we switch to another thread and nothing happens, and this is a very common scenario if you're using like databases and you have a connection pool, and your connection pool, the number of connections is exhausted, so now you need to wait until a connection is available. So basically your CPU is doing nothing and waiting, and then you switch again because the time slice ended for that thread, so forth and so forth. So in order to give you some idea of what's going on, is there is this GitHub repository where you can just run a small benchmark, and it will tell you how much does it cost a CPU context switch. Like on my laptop, with all the security features enabled right now because of all the security bugs that we have in the last 2 years, a context switch takes 1 microsecond. Before this was really, really fast, but now because of all the mitigations of the security bugs, it takes 1 microsecond. So, and to put this even in worse numbers, is that if you go on your Linux configuration and you look up how many times does the kernel does a context switch, you'll see that it will do 1,000 context switches per second. If it does 1,000 context switches per second and it takes 1 microsecond to do a context switch, it means that for every second you are wasting 1 millisecond in context switches. Anyway, to put this a bit more lightly with an example, let's look at Tomcat 9. So everyone here knows Tomcat, I guess. It's not. It's a very common, very popular project. So Tomcat 9, it's a multi-threaded application server, and the default configuration is that the max threads, like the total threads that it will allow to handle connections, is 200. So if you go back to the example that we have this API that takes 5 milliseconds to return, and now let's imagine that instead of 200 requests, we have 1,000 requests, which is nothing nowadays, because who here has an API that only handles 200 requests per second, like 1,000 is also peanuts. What happens is that, like the first second, the first 200 requests will be handled by the 200 threads, and they will return in 5 milliseconds as expected. Now the remaining 800 will need to wait for the threads to be available. So from these 800, the next 200 will be handled by these 200 threads, and now their time will be 5 milliseconds, which is the normal API time, plus 5 milliseconds that they had to wait before. And the remaining 600, again, they take 5 milliseconds execution time plus 10 milliseconds waiting time, because it starts to grow. So you can imagine that it becomes like a snowball. And when I said here that this hypothetical load is 1,000 requests, I didn't say 1,000 requests per second. If it would be 1,000 requests per second, then we get a snowball effect. Like the waiting time will start to grow until nothing on your system will work. So at max utilization of your application, what happens is that your CPU is mostly waiting, which is a waste. Like you have like big machines, you go on your cloud provider and you ask for the biggest and beefiest machine that you can find, and it's doing nothing, it's just waiting. So what we should consider is like, we should consider non-blocking I/O. So I'll use here Vert.x as an example to explain how non-blocking I/O works. So we have a concept of an event loop. So event loop, if I have to put it on pseudocode, is a while true loop, like a forever loop. that only does one thing. It looks for events, and if there is, like say, there is an event there, like a request comes in, and it passes to a request handler. A request handler is just a method call, so it's really fast, and you don't need threads, so you don't need to do context switching or whatever. This request, let's say it's a normal web API, needs to do a couple of things. First, it needs to go like to an authentication handler, for example, to verify if the request is valid. So this is all done in memory. It's just a method call and then returns. The request handler then calls the DB handler to go to the database to fetch some data, and here things are a bit different. Like before you would say, go on the database and get me this data, and you wait. Now, what you need to do is that the DB handler will say, please, event loop, here's a message that I want you to send to the database. So it goes to the event loop. And when the database returns the data, then give it back to me. So it goes back to the DB handler. Once the DB handler completes the processing of the data, so the code didn't block, it just went to the event loop, it came back. Then we get the state back, go to the request. Okay, now we have the data. We can format it in JSON, for example, and we can return it. And the event loop now will pass it back to the socket that the HTTP connection and returns it. So what it means is that I have my CPU always 100% in use. It's never waiting. And this is very important because one big difference between Vert.x and other frameworks is that like Node.js, for example, is that Node.js will have only one CPU in use. Vert.x will use all the CPUs that you have, because on my laptop, because I have eight cores, I will have 8 event loops. So all the CPUs will be used. So how can we measure this? Because we are talking about, I'm just saying, well, non-blocking I/O has better benefits than blocking I/O, but we need to measure it. So benchmarking is one way to do it, and we all know that benchmarking is hard. And what is even harder is getting like a meaningful benchmark, because I could write my own benchmark and run it, and then everyone or someone would say, well, you wrote it, so you have it biased for your use case, and you run it on your hardware, so you tweak the system on your benefit. So what I found is that there is this website called the Tech and Power Frameworks Benchmark, which is quite interesting because they have like more than 500 contributors. They already merged like more than 4,000 pull requests. They have more than 11,000 commits. And they already test more than 650 different frameworks. And this is really interesting because it's a really good workbench to do experiments. So if I want to do the experiment to prove my case about blocking versus non-blocking, I can use JavaScript, which is a very popular API from the Java EE world, which uses the serverless API in a blocking API way. It's thread-based and it's written in Java. So if I have to compare the code between JavaScript and Vert.x, they look a bit different. And here is one of the biggest, the first shocks that you get when you do comparisons between non-blocking code and blocking code. Like the non-blocking code, as in Vert.x, is a bit more length, has more lines. It's a bit harder to read. But this is just a matter of taste. Like in this example, everything was implemented with callbacks. So it's a bit harder to understand, but we could use helper libraries like the reactive extensions, Rx or Flow APIs, and then it becomes easier. And those libraries are getting so popular that everyone will be able to read them. So if we let the benchmark run on the Tech and Power hardware, we see the results. For the same test, we get almost, and the test is, in this test, each request is processed by fetching multiple rows from a simple database table and serializing these rows as JSON response. And the test is run multiple times, testing 1, 5, 10, 15, and 20 queries per request. and all tests are run at 512 concurrency requests per second. This is the table at 20 queries per request, so like the heaviest, more intensive test, and it shows that even when like the load will be like the highest on your application, using a non-blocking API just gave you 60% benefit in throughput than using a blocking API. So we are saying that just by writing non-blocking code, you can handle 37,000 requests per second, while before using blocking APIs, you can only handle 14. It's 60% difference. It's quite a lot. So, and the next quiz question is like, one cool side effect of non-blocking code is that with the same hardware, you can handle more load. If you can handle more load, it means that you need probably less hardware. So this will save your cloud bill and also save on resources, on energy for the planet. But nowadays, people talk a lot about polyglot applications. Polyglot applications are popular because not everyone likes to write everything in the same language, or the language is not the best tool for the job. Say, for example, that you are making a web application. You will use probably JavaScript. If you are doing some AI, you'll probably go with Python because most of the AI libraries are written in Python. And if you're doing a web server APIs, probably we just go with Java. So once you go with a polyglot, something interesting happens. Say that we want to make an application that says hello, ni hao. I think that's the way to pronounce it. So what happens here is that like you are in the Java context, then you need to go on the scripting engine context to get, for example, the context object. The scripting goes back to Java to get the object reference from memory, go back to the scripting to get the response object, that gets back to the Java to get the object reference from memory, and so forth until it finally sends the response back to your client. What happens here is that lots of conversions need to be done every time you go from language A to language B. And this switch between languages is a big performance bottleneck because say, for example, that we're talking about the JVM. The JVM only knows how to optimize Java code. It doesn't know how your script engine should optimize code. So it's up to your script engine to do all the optimizations on the script side. So there are two different engines that are fighting to do the same work. So in a nutshell, once you go with polyglot on nowadays, there will be lots of object conversions. So if there are object conversions, it means there will be lots of garbage being produced by your JVM. So you're going to have like constant switching between the engine and the JVM, so pretty much like the context switching. So it will not be well suited for performance. And the JIT will stop the optimizations at the language boundaries. So people will say, well, but Node.js is fast. How about Node.js, for example? So Node.js suffers exactly from the same problem because the architecture is pretty much the same as with the JVM. So in JavaScript, there's only the Node standard library, and then there's like several components in C++, like the Node bindings, the Chrome V8, the JavaScript engine itself, and the JavaScript engine itself can only optimize the top of the chart. So to put this in perspective, the JIT optimizer, both on JVM or in V8, can only optimize a tiny bit of the code, like the top part, not the full application. So it's like an iceberg. So if you use Tech Empower again to look around, where is Node.js in the Tech Empower? Because people keep saying like how fast it is. So if you look on the Tech Empower, we'll see that, and I zoom in here, like it ranks at number 89. The first entry that shows up there, and the performance is like only 20% of the best framework on this test. So the question is, can we make Polyglot faster now? Well, the answer is yes, we can, because there's this new cool project called GraalVM. And GraalVM is a polyglot VM. So GraalVM will be able to work with Scala, Java, Groovy, JavaScript, Ruby, R, Python, C, C++, Rust. Because what they did is that they remove the boundary between languages, so all languages can be optimized and run on the same JIT compiler. So how do they do this? So basically, they just have like a standard JVM, and the JVM has this interface called the JVM CI, JVM compiler interface. So this JVM CI allows them to replace the standard compiler, JIT compiler that is built in, which is called C2, and they replace it with their own called Graal. Graal then compiles every languages into this representation called truffle, and by doing this, then they remove all the boundaries between the languages, so all the code will be able to see all the other code. So the optimizations can be applied to the full application, not just one specific language. So in a nutshell, it's and here I'm going to repeat a slide I showed before, but with a small difference. Like there won't be lots of conversions because there aren't conversions anymore, because the code between languages can just see each other. There won't be switching between Engine and Java anymore. It will be well suited for performance because of the previous two. And the JIT compiler now can see the whole application, so it can make even further optimizations. So as a proof of concept to explore this concept, we created this project called ES4X, which stands for JavaScript for Vert.x. And what it does is, because we wanted to use a polyglot approach in our application, we have a GraalVM-based application that uses a Vert.x to do all the I/O and event loop as before. And now we have just added a common JS and ECMAScript module loader, so we can use modules from NPM. So for JavaScript developers, this will be like a walk in the park, because it's the way it works on Node. And it also can use the debugging and profiling tools using Chrome DevTools, which is offered by GraalVM itself, so we didn't have to do anything ourselves. So just to let you know how simple the project is, it uses GraalJS to be the fast.js runtime, Vert.x for the I/O and event loops again, and GraalVM for the JIT. And if you look at the source code, there are something like 1,700 lines of Java code and 1,200 lines of JavaScript. So in total, the whole project is 3,000 lines of code, and probably it's getting lower and lower because more features are being added to GraalJS that we don't need to write workarounds. So it's really minimal. So I did the test. So I compared the Node.js with ES4X. So here we see a small difference. Like before, Vert.x code would be longer than blocking code. In this case, Vert.x code in JavaScript is shorter than Node.js because of the reason I just said. Like Node.js needs now to use a cluster module and fork the process to use all the CPUs, and Vert.x JavaScript one doesn't, because it's all handled for you. So the application is very simple in this case, because I just wanted to show the code. It's just doing an LO printout. So if you run this was pushed to Tech Empower, and if we now look at the results, we see that JavaScript, that was on the rank 89, if I remember correctly, is now showing on rank 6. So there is a big improvement there. And in another test, it's very interesting to see that ES4X is even better than the Vert.x web Postgres, which is the exactly same code but written in Java. So this shows you that GraalVM is doing very good optimizations, because first it managed to optimize a mix of Java code and JavaScript code, plus it even optimized it further because the performance is better than the Java reference implementation. And we're talking about 1,500 extra requests per second in this specific example. So I'm talking about, yes, Polyglot with GraalVM is fast, but what about latency? Well, GraalVM also, Tech Empower also lists latency, so it's pretty cool to look at the results. So here what I did is I just filter out the projects using Vert.x and the best blocking JAX-RS implementation, which is the Undertow Jersey using the CARI connection pool, and just put node there for reference. And now you can see that at peak, at the highest requests per second and heaviest load on your application, GraalVM is doing so much for you that the latency is like the lowest, even lowest than a pure Java version of the same benchmark. And by the way, we need to be fair here. Like the pure Java implementation of the benchmark is not, in this case, is just running on stock Open JDK 11. So probably if we would just run both with GraalVM, the results will be the same, because it's pretty much the same code. It's just written on a different language. So in order to put a conclusion to this presentation, what I want you to take home is that latency is not a really problem. It's a symptom of your system. You can use non-blocking to get the full capacity of your CPU. And I would say, well, use Vert.x, of course, because it's a project I work on. But yeah, you are free to choose. And if you're working with Polyglot, Polyglot is fine. And my recommendation is like use GraalVM for the Polyglot JIT, because it does all these optimizations that it makes it really possible to use on applications. And remember, like when people say that Node is fast, well, it's fast in specific cases, of course, but if you are working on server applications, long-running processes, probably you should use ES4X, of course, because it's the project. So if you want to chat with me or anything, you can follow me on all these things. So Twitter, GitHub, LinkedIn, and I have here the links for the projects I just referred in the presentation. And thank you.